All right, good morning, everyone. Welcome back. I know that pretty much every one of you, except maybe one or two, did as I asked and enrolled in my math lab, so that's awesome. I am very glad that y'all took that motivation and enrolled so that you've already got access to your course materials. Just a heads up, I've been having trouble with one of my math lab courses, my math lab courses. That sounds weird. It's not y'all's, but it wouldn't surprise me if we start having a couple of issues with y'all's as well. So please just, if for some reason your textbook isn't loading, or maybe you try and log in and it says you don't have credentials or something, try again. If you try 2 or 3 times, maybe come back in an hour. Like I said, the website isn't perfect, especially the first week of class. Their servers have, been doing nothing for 3 or 4 weeks, and now all of a sudden it's the first days of many colleges' semesters, so they can get bogged down. But I don't want to spend too much time ranting and raving about that stuff. I just want to do, like I said, a really lightning fast review of a couple of topics. Nothing too crazy. Again, the reason I'm not going to be doing a 2 or 3 day review is because, first of all, we don't have time, and second of all, I gave you access to other materials, including some of my math lab problems and external documents and websites to help you with that stuff. But 1 or 2 things that I feel like would be very important for us to discuss before really getting into the true course materials is, first of all, interval notation. This is something that will be used throughout the semester, not for, say, every single problem, but we will have a lot of problems where this is relevant. So this is just another way of describing an interval for a solution generally. So we can draw these using a number line, or we can write them in what we call inequality form, or we can use interval notation. So there's 3 different versions of how we can answer something, but interval notation is how we like things in calculus and moving forward. And because this class is pre-calculus, we got to prepare for that. So interval notation is generally, I don't even want to say generally, is always written as the furthest left number, then a comma, then the furthest right number. And surround these with either parentheses and or brackets, depending on the original inequality symbol. Special note, infinity is always a parentheses. So answers in interval notation look something like parentheses 2, 5 bracket. They can both be parentheses, they could both be brackets, or it could be a mixture of them. But whenever you use positive or negative infinity, infinity is always out of our grasp. If you reach as far as you can to try and grab it, basically it just moves out of your reach, and that's how infinity works. It's a theoretical number. It's just we get to deal with it a lot in higher mathematics. So because we can't ever touch infinity, we use a parentheses. A parentheses means it's just out of our reach, whereas a bracket means we can touch it, we can include it. And that's when we have the less than or equals. That's when we would use a bracket. So when we see, that was weird. It took a second to start working. When we see, and it switched color all of a sudden, whatever. When we see less thans or when we see greater thans, that means we're going to use parentheses. When we see less than or equals, or we see greater than or equals, that means we're going to use one of the brackets, whichever one is relevant. So what I'm going to do is I'm going to give you the inequality form, the graph form, and I'm just going to abbreviate IN for interval notation. So 3 different forms for a couple different answers. So if you solved an inequality and you came up with an answer that looked like x is bigger than 5, as a graph, if you were just doing this by hand, you only need to see an absolute one single number on that, and that's the 5. because this was a greater than symbol, because it did not have the or equal, we can't touch the 5, we can't use the 5. It goes up to 5.00001, but not actually 5. So that means we're going to put a parentheses on it. And greater than means we're going to shade to the right. So we would shade to the right. I like to put an arrow on the far right side signifying that it goes on forever and ever. And then we parentheses at the 5. I just hit something weird. Okay, so the interval notation, again, it's furthest left, furthest right. That highlighter's a little thicker than it's supposed to be, but I don't want to have to erase that. You get the idea. Furthest left, comma, furthest right. So the furthest left on the graph is the 5. So that's the first number that we would write. We would write the 5, then a comma. And this thing is shading, it's going forever and ever and ever to the right. We're going to what we call positive infinity. And you have to have the signs of your infinities correct. You don't have to write the plus. I don't have to do that. And in fact, if you do it in my math lab, it'll probably mark it wrong. So don't do that. Because the 5 had a parentheses here, it also gets a parentheses here. Because this is an infinity, they always get parentheses. And again, the reason this 5 had a parentheses was because this did not have the or equal. If it had the or equal, then it would have instead been a bracket. But it didn't, so it doesn't. So in stark contrast, if I had x's bigger than or equal to 5, I'm going to do this super quick. It'll be number line 5, and we'd still shade to the right with an arrow going right forever. But now it's a bracket on the 5 instead. And the interval notation is still 5 comma infinity with a parentheses on the infinity, but now a bracket on the 5. You may be coming from a school or a class or a teacher where they taught you open and closed circles, and we will see those in 2-dimensional graphs, but we never really use them in 1-dimensional graphs at this level. It's not wrong, it's just kind of a weaker notation in 1 dimension. The reason we like the parentheses and brackets in this form is because they will literally be exactly the same. If I use an open circle and a closed circle, you have to know the difference. Now, granted, you still have to know the difference because, again, we will get into this stuff with 2 dimensions sooner than later. So just be aware that an open circle looks something like that. And when I call it a closed circle, that means it's a shaded circle. It means you actually would shade it. So the other version of graph, the top one would have an open circle around that 5, and this one would have a shaded or a closed circle around the 5 on the bottom one. You use closed circles for brackets, you use open for parentheses. My math lab is not going to give you that as an option, so please understand this stuff because it's what you'll have to do. All right, let's do 2 or 3 more. What if we had x's less than or equal to, I don't know, 12? Number line, just got to put a 12 up there. 12, not 2. Sometimes when I hit undo, Word moves on its own. Sorry for that. Less than means we shade to the left, and we're going to shade forever because there's nothing saying otherwise. Arrow for the forever aspect. And then it has the or equal, so we bracket it. Don't bracket it facing the right. Make sure it's facing the shaded region. That's important. Then the interval notation, you have to be very, very careful here. This is going left forever. The interval notation starts with the furthest left number, so that's supposed to be negative infinity. Not infinity, negative infinity. Then comma, and we're shading right, we're shading right, we're shading right, until we hit positive 12. Infinities always get parentheses. The 12 gets a bracket because of the or equals. If we had x's, let's go less than, and let's do a different number. X is less than, I don't know, negative 50. Number line. Here's our negative 50. We'll shade to the left forever. Arrow saying it's going on forever. Because there's no equals, we do a parentheses or an open circle if you were doing this by hand, but again, my math lab's not going to allow that. For the interval notation, we're going left forever, so that's parentheses, negative infinity, comma. Again, parentheses, because that's always the case for infinities. You can never touch infinity. Not even the craziest, most brilliant mathematician can touch infinity. Buzz Lightyear can't touch infinity whether he claims it or not. Sorry, terrible joke. And then we're going up to the -5, and the -5, excuse me, had a parentheses, so parentheses. We can also see these listed as what we call a compound inequality. A compound inequality means that the x is surrounded by two numbers, something like, I don't know, -10 is less than x is less than or equal to 45. So this says x is sandwiched between these two numbers, so well, that's literally what the graph would look like. You do a number line, you'll need both of those numbers up there. Now make sure they're in the correct order. The -10 and the 45 could be on opposite sides as long as the inequalities were respectfully true. So in other words, these would have to point in opposite directions if I swap the order of the 10 and 45. So -10 does belong on the left, 45 does belong on the right. We're going to shade between them because the x is between them. There's no arrows going left or right forever this time. Now the -10 had did not have the or equals, so it gets a parentheses. The 45 did, so it gets a bracket. You just have to pay attention and learn the lingo. And if you're rusty with the lingo, guess what you need to do? And I'm going to say this all semester long, practice. Practice makes perfect. I can't learn anything until I practice it. So interval notation, there's not going to be any infinities because we didn't go left or right forever. Furthest left is the -10, comma, furthest right's the 45. There was a bracket on the a parentheses on the -10, I was looking over here, and a bracket on the 45. So that's interval notation, a very important thing to know moving forward because we will use it for tons of problems. Not every problem, but tons of problems. You'll see this used in two-dimensional graphs when we talk about things like domain, range, where they're increasing or decreasing or where they're constant, as well as some other applications. Okay. Next up, absolute value, just really, really quickly. And I forgot to do something at the beginning. Please don't push any of that down. Yes, sometimes it pushes that down, sometimes it doesn't, and you can never tell when it will or won't. So I got lucky that time. Absolute values. Something that we think of quite often without actually doing. A lot of the times we'll talk about the size of a number, but not really the sign of it. And that is really just the absolute value. So if you have, sorry, I have to think about this for a second. Where's my symbol? There it is. If you have the absolute value of 5, oops, wrong button, there we go. This would be 5. If you had the absolute value of -5, it would also be 5. Because the absolute value just makes the argument positive. This doesn't mean that every single number that has an absolute value, the answer would be negative though. There can be problems with absolute values that have answers that are negative. So be careful. Things like if I had negative absolute value, I keep forgetting to hit shift there, of -5, and in fact, I'm going to use different colors to demonstrate this problem. I want to make this one default to black, and I want this one to default to red because reasons. All right, so if you had the negative, then the absolute value of -5. So again, just color coding for reasons. The blue part, when you take the blue part, that's the absolute value of -5, which is +5. But that red negative I have not processed yet. So the blue is the blue. The absolute value of -5 is this +5. Again, this right here gives that, but there's still that negative that's on the outside, which, guess what? The -5 is just -5. So that shows you that there can be negative answers with things that had absolute values. You have to be careful. A lot of people might accidentally think these two negatives cancel each other out, and they don't. You can't cross operations across an absolute value because of PEMDAS, because of order of operations. And in fact, even though I feel like I shouldn't have to do this, PEMDAS, parentheses, exponents, multiplication, division, addition, and subtraction. Please excuse my dear Aunt Sally. Please remember there are only 4 steps. There are only 4 steps. There are only 4 steps. 50 exclamation marks after that. 6 letters, 6 steps, right? Wrong. Wrong. But my friend on Facebook saw this problem and they said it was 6 steps. And wrong. Your friend on Facebook's wrong. Social media sucks. Stay off of it. Because multiplication and division go hand in hand. They're 2 sides of the same coin. They're heads and tails. So that is just 1 step. You do them from left to right. If you see 50 divisions and then a multiplication at the end, the far right, you would do the 50 divisions and then the multiplication. The same goes for addition and subtraction. They're just opposite sides of the same coin. So please get that right. You don't want to be missing problems in precalculus because of arithmetic errors. All right. Go to the internet if you need examples of that. I'll do a very, very, very short, simple example. If you had something like 5 minus 7 plus 3, someone on Facebook's going to say 7 plus 3 is 10, and then 5 minus 10 is negative 5. And that's wrong. You've got to do the subtraction first because it's written first. 5 minus 7 is negative 2, and then negative 2 plus 3 is actually positive 1. Your friend on Facebook is wrong. I'm sorry I have to pick on that. Back in the days before I canceled social media for myself, I remember seeing things like that. And I mean, it's what you expect, but it's just so many people would get passionate about their wrong answer being right, and they would never allow themselves to hear someone out who might actually understand the properties. But that's the internet. That's what it is there. We got right and we got wrong. Your exponential rules. You know what? I'm actually going to peek into the textbook real quick because I want to use the same lettering that they use. There's 50 million ways I can write this, and they use B's, M's, and N's. Okay, cool. So if you have something like B to the M times B to the N, so that means same base, and you just add the exponents. So these are multiplying. If you had these on top of each other, you would subtract the exponents. I'm going to run out of room on this page. So there's 2 different ways you could do this, though. You could put the base in the top and do the top exponent minus the bottom, or you can put the base in the bottom and do the bottom exponent minus the top one. Now, why would you want to do this one of 2 different ways? How do you know which one to do it? Put the base where there's more of them. So in other words, if you had x to the 5th over x to the 2nd, if you have more x's in the top, then put the x in the top and do the bigger number minus the smaller number. If you have more of the x's in the bottom, say it was x squared over x to the 5th, so there's more in the bottom, you put the x in the bottom and you again do the bigger exponent minus the smaller one. It just avoids having to deal with a negative exponent because, well, that's not always too fun to deal with, but we do have a rule to get rid of them, as we'll see shortly. Next up, if we have b to the m to the n, that would be b to the m times n. These are being multiplied. A lot of people confuse this top left rule and this, for now, top right rule. How do you know when you're supposed to add them and when you're supposed to multiply them? Look at the bases. If the bases, if there's multiples of those bases, if there's 2 or more of them, that's when you're going to add them. When you see a base only once and then its exponents, these even look like they're multiplying each other, in my opinion. So I just feel like this is very natural. But some people will still want to go back and multiply these, and that's not the case. You can have 2 different bases being raised to the same exponent, and then you just distribute that exponent. You could have a fraction of bases being raised to the same exponent, and then again you just distribute the exponent. Some of these rules, especially I think these right three rules, are actually pretty sensible. It's just when you mix the top left and, again, for now, the top right one, that people start to get confused. But if you actually write these out in what we call expanded form, if you had like x squared times x to the fifth, if you wrote x squared as 2 of these x's and x to the fifth as 5 of them, you would now have 7 total. You could just re-squish it into x to the 7th. That's essentially the proof that you add the exponents. The same thing can be said here. If you add x squared to the 5th, that just means you're going to write x squared 5 times. X squared times x squared times x squared times x squared times x squared. You'd be adding all of those 2's. Be adding them 5 of them. 2 plus 2 plus 2 plus 2 plus 2 is 10. And then last but not least, and I'll give you a couple of variations of this one, negative exponents mean you take the reciprocal of the base. Reciprocal means flip it. Anything in the top goes to the bottom, any bottom goes to the top. And then you change the sign of the exponent. So if the base is originally in the top, it now goes in the bottom. If there's nothing else in the top, you always need a 1. Or b to the, I'm sorry, let me not write it that way. I forgot my 1 over. So if your base was originally in the bottom, that means you're going to bring it to the top. And if there's nothing else in the bottom, you don't have to write a bottom. You don't have to do that over 1. And in my math lab, it would probably mark it wrong. That's something, if you did that on a test, I could go back and give you credit for if you pointed out to me if your work looks correct. Remember, you have to show your work to get partial credit on things. And that would be, I'd give you full credit because I'm not really too worried about an extra over 1 here and there. But again, you'd have to let me know, and I'm not going to do anything like that for homework. All right. One thing to be very mindful of. Here. Be careful here. What if we have -2, no, let me not do a 2, let's do a 3. -3 to the second versus -3 to the second, but one of them has a parentheses and the other doesn't. Parentheses and exponents have priorities. So when you have a parentheses, that says you're supposed to be thinking about this all together and then squaring it. So this -3 squared is actually -3 times -3, which would be +9. But this -3 squared, because there's no parentheses, mathematically the negative is not part of the exponent, believe it or not. This negative is not part of the exponent. That's the way it works. So this is really -3 times +3. The negative is just this negative, and then we're squaring the 3. A negative times a positive is a negative. Major difference there. Now here's what's interesting. When your exponents are even, it leads to different answers. If your exponents are odd, though, you actually get lucky. Let's say we had -2 to the third versus -2 to the third in parentheses. So this first one is just a single negative, then 2, 2, 2. -2 times +2 is -4. -4 times +2 is -8. But this other one, that's 3 of these negatives. -2 times -2 is +4. +4 times -2 is -8. So you actually get the same answer, but the work looks different. If I gave you a problem in Precalculus, which I'm not gonna, and all it was this, if you had that answer right, I'd tell you you have to show your work because it's so simple to make sure that you fully understood it, because you might just get lucky. Don't just flip a coin on the even ones, though. Make sure you understand when to repeat the negative, when you don't. How are you going to understand that? What do you think I'm going to say? Practice. Okay. So watch out for exponents dealing with negatives. Last thing I want to talk about for review for now, I will bring up a couple other topics that are quote review when they become more relevant, but I just want to get a couple of things out of the way that tend to be blanket across the whole semester. Radicals. Your radicals, your tubulars, your gnarlies. No, not surfer lingo. This is a square root or a cube root or a fourth root or a fifth root, things like that. So not covering all the basic rules of how square roots and cube roots and fourth roots work. You should definitely know that. And again, if you don't, there's examples. I'm talking about the rules of simplifying things like, what if you have the nth root of a over b? What can you do there? Because you're not allowed to leave fractions under radicals. You would have to split this up. And you can do this with divisions and with products. So that would be the nth root of a over the nth root of b. Or if it was a product, if you had the nth root of a times b, you can make that the nth root of a times the nth root of b. Now, these are a two-way street. You can break up a product, or if you have multiple radicals, you can squish them together. This one especially is wonderful as a two-way street. This first one is also a two-way street, but I will admit more often than not, we're usually splitting it up. And in addition, all exponent rules apply. All of the rules I just wrote earlier apply because radicals are, spoilers, literally exponents. These are the same thing, basically. Radicals are just a different form of an exponent. And that's because of this important rule that if you have the nth root, I gotta make sure I get my n's and my m's good looking, of b to the mth power. In fact, I'll make that one blue for emphasis. There we go. This is the same thing as b raised to the m over n. Oop, I knew I could shift those, but there we go. These are the same thing. This is a very important rule that, again, will be used all semester. The left side is what we call the radical form. The right side is what we call the rational exponent form. Rational exponent, it means that the exponent is rational. The word rational means fraction. In math, there's a lot of words that have different meanings than what you might think in the real world. In the real world, we think, oh, rational is like a type of thought process, to think rationally, to make logical decisions, that kind of thing. In math, rational means fraction. We usually use the word rational for messy, ugly fractions that have variables littered all over the place. But in this one exception, we talk about rational exponents just as numbers of fractions. Now, they could still be variables, but we're not going to see that in this course. That would be really ugly, at least until chapter 4, and even then, it's a very simplified version of it. So I think that will be good enough for the review just for now. Like I said, there's a couple more topics that we will take a very, very quick approach to like this in the future. But for now, that's going to be it. Remember, you are responsible for covering anything that is a review material, anything I'm calling review, anything from that review homework. And if you remember, I said that if you complete with, I believe, an 85 or higher, that review or prereq homework in my math lab, that I would give you 5 bonus points towards test 1. And by the way, the due date for that will be test 1, test 1's date, which I don't have for you yet. So you got plenty of time for now. All right. 1.1. And I believe that section is just called graphs. Let me make sure. Yeah, graphs and graphing utilities, we can just call it graphs. That's fine. Now, you will notice there's not a homework section for this. And that's because this is, again, actually a review section. I find it interesting because 3 or 4 years ago, we didn't call it a review section, but now we do. times change, right? But I still just want to really quickly cover what is in this. So you won't find any homework on this material, and you really won't find any test questions on it because of that. But what did that say, 1.2? That was just me hitting entering, and it said 1.2. Let's see. Let's draw up our basic two-dimensional coordinate system with an x and a y axis. These are divided into 4 sections. 4 means quad, so we call them quadrants. For reasons involving trigonometry, the way that you move in degrees counterclockwise, starting at the positive x-axis, we call the top right area quadrant 1. We call the top left quadrant 2, bottom left quadrant 3, and the bottom right quadrant 4. You can use Roman numerals like I've done. You can use regular numbers. Nobody cares. Traditionally, they're done that way. This point where the axes cross is called the origin, which, by the way, again, that horizontal line is known as the x-axis, and the vertical line is known as the y-axis. They're the starting points, if you will, in each cardinal direction. This is not the only coordinate system in the world that can be used. This is known as the rectangular or Cartesian coordinate system. When you get into fancier math involving like polar coordinates, you can have a rotational coordinate system. We'll save that for another day, not in this class. What's the beauty of this? The beauty of this is that we can describe any and every single point in this two-dimensional plane expanding forever to the right, forever up, forever down, forever left, with a pair of numbers. Any point on this coordinate system be described with a coordinate pair. I'm going to underline that. Which looks like a pair of parentheses with a comma between them and 2 numbers. It kind of looks like interval notation, and here's the unfortunate side of things. It's not interval notation. This has absolutely nothing to do with interval notation, in fact. This is just a number that tells you how far to go left and how far to go right. So your x is how far left or right, y is how far down. So I'll just put a single point up here, and let's have it be right here. And on the axis, I'm going to go 1, 2, 3. 1, 2, 3, 4, 5, 6. So that's a 6. That's a 3. So that point, that coordinate is 6. I'm sorry, I have that backwards. I was looking at the 6, pardon me. Would be 3, 6, because we go right 3 and then up 6. You're starting at the origin, and you'll know if these numbers are negative because you'd go left or down. So it's always how far left or right, then how far up or down. We say x and y because that's how far they travel along their respective axes. A basic way of graphing equations is to use series Sorry, I got distracted at home. A basic way of graphing equations is to use a series of x values. Now, why did it tab over correctly the first time but not that time? Always fun. A series of x values going in the same multiple. What I mean is going like x equals 0, 1, 2, 3, 4, 5, or 2, 4, 6, 8, 10, or -3, -2, -1, 0, 1, 2, 3. That's a basic way of graphing equations. Basic. I'm going to highlight the word basic. Very, very basic. This is how we generally learn what a type of equation looks like, but then from there, we want to extract a more efficient method of graphing it. Because if you just say, all right, I'm always going to go from -3 to +3 in intervals of 1, that's not going to work for every single graph. Trust me, we will see that that's a problem moving forward. So again, this is just usually used to find out what a graph looks like in its basic form. But when we go to study these more extensively in chapters 2 and 3 and 4, we'll get better ways to graph them without just plugging random numbers in. We'll get things like asymptotes and vertices and intercepts. So example, oh, that was weird. Graph y equals x squared plus 3. Now, I can certainly just give you this, just graph y equals x squared plus 3, and you could say, well, let me try a bunch of different numbers like Mr. Beckner said. Maybe I need to go from 0 to 10. Maybe I need to go from -80 to -42. How do you know what range of x values would be good to use? Well, a little bit of practice, but also some other complications. And I just realized that when I tab or enter over there, that this thing got all goofy. Draw, erase. It's not going to be a big deal though. I just got to fix that. Oops. Not a huge deal. Not a big deal. 1, 2. There we go. That'll work. Okay, so back to the example at hand. Graph just by doing a series of values, but I will tell us this time, and in this introductory section, my math lab will as well, we're going to use x equals -3, -2, -1, 0, 1, 2, and 3. This is a great starting set of values to use. But again, it's not the end-all be-all. So what we're going to do is create a table of values. In a table of values, instead of doing coordinates, so like this point 3, 6 in parentheses would just be a 3 on the left and a 6 on the right, because the left column represents the x values, the right column represents the y values. Now we're starting out with these -3 through +3, so those are all x values. They have to go on the left. Probably going to need a little more. -3, -2, -1, 0, 1, 2, 3. I will show the work for some, maybe all. Let's see what I want to do. So we're starting with these black numbers over here, and we're going to plug them into the equation. How do we know where we're plugging it in? We're plugging in for x, of course, and then we'll see what y turns out to be. So when we do our work, we'll get y equals, for this first one, -3 squared plus 3. So I'll use blue for the substitution. -3 squared plus 3. Now notice that I wrapped it in parentheses. When you plug in negatives, the rule of thumb is you probably want to wrap a parentheses around it, because without the parentheses, remember that thing we were just talking about in the review earlier? Be careful of having a parentheses versus not having a parentheses. Hey, there's a reason I just reviewed it, because the issue is already at hand. So this is the case where the negative is repeated, so that negative will cancel out and you'll get a +9. And +9 plus 3 is 12. So I'll use red for the answer. That was 12, so that's 12. We now have a completed coordinate pair, -3, 12. So if we had our axes drawn up, we would start at the origin and we'd go left 3 and up 12. And I'll stop scrolling around so much now. Someone has a question. So I'm not going to say you'd lose partial points because of that, because quite honestly, I probably wouldn't catch it if your answer is correct. I'm usually only looking for issues when I see wrong answers, but it's just a bad habit to have, because what you might do later with that bad habit is start making mistakes with it. So it's for your own good to not omit these parentheses, because it creates a bad habit that will cause errors down the line, probably. So that's a good question. Cool. All right, so I'll show the work for a couple more. Wrong color. Y equals -2 in parentheses squared plus 3. -2 squared is +4 with that negative in the parentheses in that manner. And +4 plus 3 is going to be 7. Y equals parentheses, oops, blue, -1 squared plus 3. That's +1 plus 3, which is 4. I'm going to fill in those answers after the fact, just so I can kind of move along. When I plug in the 0, y equals, I don't need the parentheses anymore because that's not a negative anymore. So 0 squared plus 3, which is 0 plus 3, and that's 3. And the 1, y equals 1 squared plus 3, which is 1 plus 3, which is 4. Huh, interesting. Let me start filling these out. 7, 4, 3, 4. Look at this answer, look at this answer. There's symmetry here. They both had the same answer, and look, when we plugged in the negative one, we got 4. When we plugged in the positive one, we got 4. The symmetry doesn't always have to be perfect around the x numbers just being positive or negative, but that's interesting. Let's see if that keeps happening. So y equals 2 squared plus 3, which is 4 plus 3, and that's 7. And then y equals 3 squared plus 3, which is 9 plus 3, and that's 12. So yeah, when we plug in the negatives and the positives, we're getting the same outputs. The same output can be seen from -3 and +3. The same output can be seen from -2 versus +2 being plugged in. That has everything to do with the fact that when you square a negative, the sign goes away. So that's what leads to something we call symmetry that we'll study pretty extensively in this course. It's great to have symmetry because it can lead to shortcuts of things. Now, just because there was an x squared doesn't mean that symmetry is seen. If there was somewhere like a plus 5x, that symmetry would fall apart. But this is great when we do see that. So what's our graph look like? Let's see if I can squish this over here. I don't have any negative y values, so I'm going to make this a very top-heavy graph, as you can see. My x values are between -3 and 3, so that's all I really need to label on the x-axis. Try and space them as best as you can in your own notes, like I am. I don't expect perfection. A ruler would be awesome, but I don't mandate it. Remember, in your homework and tests, this is all done digitally. My y values have a maximum of 12, so I need to go up 12. I don't have to go in increments of 1. I can go 2, 4, 6, 8, 10, 12. I can go 5, 10, 15. But that wouldn't really benefit me here because the numbers don't get outrageously large, and I'd have a lot of in-betweens. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I'm only going to label some of these. I'll label 12. I'll label 1, 2, 3, 4, 5, 6. And then yeah, that should be good enough, I think, for us, just the 6 and the 12. So -3, 12. And this -3 and 12 written as a table of values, it would be the same as if it was this way. Those are the same information, just written different ways. When I've got 7 different coordinate pairs, it's going to be a pain in the butt to keep writing these commas in parentheses, don't you think? So I like tables of values for larger sets of data. All right, so -3, 12. Start at the origin, left 3, up 12, and that would be right here. Start back at the origin, -2, 7. That's left 2, up 7, which is about here. Now you'll notice that my widths are a little larger than my heights. That's fine. You can scale these things however you want as long as you're consistent. I can't change the widths of the y-axis along the way. Like I couldn't say this was 1 and then this up here was 2. That would be a bad idea. Next up, -1, 4, left 1, up 4. Then we have 0, 3. Zeros you have to be careful with. I'm not just going 3 to the right. I'm going 3 up because the 0 is in the x position, so we don't move left or right at all. So left or right, nothing, up 3. Reset to the origin, 1, 4, right 1, up 4. Reset to the origin, 2, 7 is right 2, up 7. Reset to the origin, right 3, up 12. And you should have seen a shape that looks like this before. This is the shape of what we call a parabola. It's the standard form of a quadratic. Parabola is quadratic, different name, same thing. What we want to do with these dots is show that the pattern persists not just for the whole numbers, not just for the integers, but all the in-between. But we don't want to do this. I'm going to switch to red for a second. Don't do this. We don't want to do this. We do not want to connect these just with several straight, rigid lines and make it look like a bunch of different V's and things. That's not how to do things. Smooth, bending, this is a curve. So it starts out kind of steeper, but then as you get closer to the x equals 0, it flattens out, and then it turns around, and then it just keeps getting steeper as you move further right. This is not going to be looking perfect, but it's pretty good for my artistic ability. With a tablet, I can't look at while I write. But this is not how I would like an answer, because this makes me think it's only true from -3 to +3 in terms of the x values. This pattern consists forever unless you're told otherwise. So I like to extend past these points a little. That was not the best extension. Let's try better. Try harder. There we go. Kind of just getting a little steeper as we go. And then an arrow signifying that this goes on forever and ever and ever. So there's our shape. We will study these quadratics, these parabolas, more extensively in chapters 2 and 3. For now, we're just taking a very simple-minded approach to graphing with these coordinates. And that's it. Okay, a couple definitions. One definition with kind of 2 versions of it. Intercepts. We're going to talk about intercepts all semester. We're going to use intercepts all semester. Intercepts are great because intercept, notice that word sounds like intersect. There's a reason for that. Because an intercept is where a graph intersects an x or a y axis. How do you know which? The name tells all. An x-intercept, underline. This is going to occur, or occurs, where a graph crosses the x-axis. Coordinate of the form. It's always, you have your pairs of parentheses with a comma between them, question mark, comma, 0. Versus the y-intercept, which you can probably guess occurs where a graph crosses the y-axis. And the coordinate is of the form, just swap the 0 and the question mark, 0, comma, question mark. What I'm saying by is of the form is the fact that the 0 is opposite the name. That's the important thing here. That's the biggest takeaway. An x-intercept has a y value that's 0, a y-intercept has an x value of 0. I think this should make complete sense if you actually analyze the scenario. Look at this previous graph. Look at this point right here. Look at this point right here. We're crossing the y-axis. And I'm going to erase this in a second because I don't want it up there permanently. But this is where we're crossing the y-axis. That means we did not move left or right at all. If we don't move left or right at all, that forces the x value to be 0. So this would be a y-intercept, and it has the point 0, 3. The x is 0, the y is whatever the height is. If our graph was up here, then this would be our y-intercept, and it would be 0, 10. Click, 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 click. There we go. This graph actually does not have an x-intercept. This graph never crosses the x-axis. That's possible. So let's see some examples. Identify intercepts. A, I'm going to draw up a graph. I'm not going to put a lot of numbers on this graph. We're going to do a downward facing parabola this time. Let's do boom, boom. And I'm just going to describe that this height right here is a 4, this position over here is a -5, and this position over here is a +5. Those are both -5 and +5 there. So the x-intercept now I said x-intercept, but here's the thing. Look carefully. Where are we crossing the x-axis? I'm going to erase these circles in a second. It crosses the x-axis right here, and it crosses right here. There's 2 of them. So it's actually x-intercepts, but I'm not going to change my abbreviation. You can have more than one of each type of intercept for graphs. So these points they're involving those -5s. So that's left 5 for the left one, and up or down nothing. If we don't move up or down, it's a 0. But it's not 0, -5, it's -5, 0, to make sure we move left 5, then up or down nothing. Remember, the first number is the left or right, the second is the up or down. But then there's a second one, so I'll do a semicolon, and to get to the second one, we go right 5, up or down nothing. So 5, 0. The x-intercepts have y values of 0. The y-intercept, well, that's what this point right here, which has a height of 4. We don't move left or right at all to get to that height of 4, so it's 0, 4. Here I'm drawing a V that kind of starts sitting on the origin. Spoilers, this is the graph of an absolute value function, which we will study lightly in this course, but we will study it. So x-intercept or intercepts, and y-intercept or intercepts, singular or plural. Got my dash there, not the end of the world. So where is this graph crossing the x-axis? Here's your x-axis. Well, it looks like the only place it crosses it is right here. That's where it crosses, or where it touches, where it intersects the x-axis. Now, to get to that point, we don't move left or right at all. We don't move up or down at all, because that point's actually the origin. Oops, red. Red, 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 red. It's the origin. What about the y-intercept? Well, the y-intercept is where we're crossing the y-axis. Here's the y-axis, and well, that's funny. We cross the y-axis to the same location we cross the x-axis. That's because we're touching the origin. The origin is the intersection of both the axes. So the x and y-intercept are the same. That is possible, but only when it's the origin. All right. Believe it or not, that's everything we really need to talk about with 1.1. We just wanted to understand the basic idea of left, right, up, and down to get our coordinate pairs, what our quadrant names are. This can come up throughout the semester. It's not super important for us, but when you get into trigonometry, if you're going to Math 162, knowing your quadrants becomes critical. Pre-Calc 1, not a huge deal, but good to know. knowing how to plot your points. If you can't do that, you're going to mess up every graph you ever make. And we do a lot of graphing in here. Knowing your intercepts, knowing which one's the x and the y-intercept, knowing where the 0 is supposed to go, very important for us. It will be a constant issue. I don't lie to you. If I tell you something's going to come up over and over and over and over and over, trust me, it does. When something doesn't come up again, I generally tell you that as well. We'll have a couple sections where I'm going to say, we're going to do this and we're never going to see it again. So at least I'm honest. What is happening? Sometimes it gets stuck in draw mode. All right, back to home then. Why is it still doing that? There we go. Erase these dots. Okay, so that's 1.1, 1.2, linear and rational equations. Not 1.3, please stop that. So section 1.2, linear and rational equations. Two things that we're going to do over and over in this course: solving equations and graphing equations. So we already kind of lightly introduced the graphing. Let's lightly introduce the solving of equations, to which most of these things you should have already dealt with extensively, but reminders. So to solve a linear equation, first step, distribute and or combine like terms. Second step, if there are fractions or decimals, multiply terms by the LCD. So you got to remember what an LCD is. Again, I'm not here to discuss fraction math and sign math and decimal math. Those are definitely supposed to be in your wheelhouse at this point. And remember, there's going to be 2 tests without calculators, so if you're rusty, you must make the effort to refresh on that. So if there's fractions or decimals in your equation, guess what? Nobody likes fractions except your math teachers, because we're sick, right? And you know, people don't have as big of an issue with decimals, but they're still a nuisance. And the good thing is with equations, because of that whole whatever you do to one side, you can do as long as you do the other, with very, very rare exceptions to that rule. Pretty much you just can't divide by 0 because it breaks the world. But because of that, if you've got fractions on both sides or decimals on both sides, or even just on one side, you can actually get rid of them with that whole just do something to both sides and be constructive in that when you do that thing, it gets rid of them. So if you find your LCD, you'll be able to have a value that if you multiply both sides by that, you're going to get rid of all the fractions because each of those fractions would reduce out perfectly. So that's for fractions. Specifically for decimals, LCD for decimals is a power of 10. Most people don't know this, but decimals, their full name is actually decimal fractions. No one wants to call them decimal fractions, so no one does. But decimals are literally fractions, but decimals are just a fraction where the denominator is either 10 or 100 or 1,000. But you don't want to convert your decimals to fractions and then do the LCD business. You could, but it's more time. Just understand what the equivalent LCD would be then. So how do you know whether you're multiplying by 10 or 100 or 1,000? The number, not hashtag, the number of zeros in your LCD is the most decimal places seen in the equation. That's how you know. So step 2 is awesome. Step 2, I cannot tell you how many students I've seen forget this. I'll teach it to them in Algebra 2, then they come to me for pre-calc and they already forgot it. Or they come from someone else and they've already forgot it. Or maybe they just were never taught it because that happens occasionally. But it is a beautiful step. It is wonderful because if you hate fractions, wouldn't you love to kick them to the curb? Now you can do this with equations. If you have a problem where the whole point of the problem is just to add a half and a quarter, you can't do it there. That's not an equation. That's known as an expression. You can't get rid of fractions and expressions because there's no equals, there's no left and right side. That's the key difference. And I will write a little example down later just to show you what I just said. Step 3, so after you've distributed and combined like terms, after you've gotten rid of all fractions and or decimals, add and or subtract terms to each side. Get the variable term on one side, and the constant term on the other side. You want all your variables on one side, you want all the terms that don't have variables on the other side. You do that by adding or subtracting the opposite of whatever you have. So if you have x minus 5 and you want to move that minus 5, you add 5 to both sides. If you had 2x plus 3 and you wanted to move the 2x, because the 2x counts as positive, you'd subtract it. Then lastly, assuming that you did clear your fractions in step 2 appropriately, you divide by the coefficient of x, and you should be done. Coefficient meaning the number in front of it. I will admit, there is no PEMDAS to this. PEMDAS, that order is absolute. You have to do your parentheses, then you have to do your exponents, then you do your multiplications and divisions from left to right in the order seen. Same for addition, subtraction. These 4 steps are arbitrary, but it is in my opinion that they are the best order of said 4 steps. What you might find is after you do step 2, you may actually create something that now would be able to be distributed or have like terms on the same side. So step 1 can actually come after step 2. These are not do them in this order always. Again, step 1 might pop up randomly after you do step 2. You could do step 2 before step 1, but it is my opinion that it makes things more of a challenge. You can do step 4 before step 3, but you're going to have a very difficult time knowing what to divide by. Trust me. Been there, done that. So these are very important 4 steps to be taken at some point in this suggested but not mandated order for you to solve simple or even more complicated linear equations. What does it mean for an equation to be linear? There's no x squareds, there's no x cubes, there's no square roots, there's no absolute values, there's no fractions with variables in denominators. They could be in the top but not the bottom, and a lot of other variations as well. They're things like (9x plus 11), 9x plus 11 is equal to 4x minus 30. So the equation is in black. I'll show me moving things around in red. Now, you're supposed to have gone through Algebra 1 and Algebra 2. You should all know how to handle this equation. Again, this is just a quick, the main reason we do a review of this is honestly step 2, because most of you, half of you, some portion of you have forgotten how to handle fractions and decimals in equations. So this one should be easy. You can move the x's to whichever side you like, just make sure the constants go opposite. So some people will just always try and have the variable be positive after moving it. Some people always like to move it to the left. It's up to you. I'm not going to tell you which way you have to do it. It's up to you. Me personally, I like to keep my variables positive. So because I have x's on both sides, there's more on the left. I'm going to subtract 4x on both sides because that's a positive 4x that's being added, so I have to subtract it. Now, if this was Algebra 1, I would do this math and then I'd do the 11 next. This is Precalculus, so I'm going to do both in one step. If you don't like it, take 2 steps instead of 1. So the blue would be your second step if you need to separate these. So my variables are going left, which means my constants need to go right. So that plus 11's got to move because that's plus. We subtract it on both sides. If you're not showing your work vertically, if you show it horizontally, that's fine. If you don't feel the need to show your work, if you can go straight to the next line because you're great at this, that is also fine as long as your answers are right. Because this is, again, on the simpler side of things. 9x minus 4x is 5x. The 11's cancel. Bring down your equals. Don't forget that. 4x minus 4x cancels. Negative 30 minus 11. Ooh, there's that sign arithmetic that you're not allowed a calculator for in test 1. So that's negative 30 plus negative 11 if you have to go the old school way of thinking. They're same signs, so you add the numbers and keep the sign. 30 plus 11 is 41. The same sign, so keep the negative. It's negative 41. Then, final step, because there was no distributions, there were no fractions originally, we started at step 3, divide by the coefficient of x. So we're going to divide both sides by 5. If that was a negative 5, we would divide both sides by negative 5, because it has to be the entire coefficient. We do that because the 5s will cancel via division. 5 divided by 5 is 1. So we just have our x left over. And then 41 divided by 5 is not a whole number. It doesn't reduce as a fraction. So guess what? You can actually do that as 41 over 5, negative 41 over 5 specifically. If you really wanted to, you could convert it to a mixed number or a decimal. Guess what? When you do extra conversions, it tends to lead to mistakes. So it is not my advice to convert this. That's perfectly fine. If you want to know a better idea of the size of the number, then making it a mixed number, which would be what, negative 8 1/5, or a decimal of negative 8.2, you can confirm those on your own if you like. Maybe that gives you a better sense of scale of the number. But again, you could make a mistake in those conversions, and that sucks because you did all your algebra right, you had the right answer, and because you did extra work, now you're wrong. Who wants to deal with that? How are we on time? We got just enough time to do this one. B, x over 4 plus 2 over 3, 2 over 3. That's what happens when you write, read, and think at 3 different speeds. You make simple mistakes. 4x equals 4x over 3 plus 1. Ramping up the difficulty immediately, putting this more on our level. And again, this is still something you should have learned already, but it's good to review. So this is an equation because of the equal sign and the left and right sides to it. So that says because I see fractions, I can get rid of them. If this equals was not here, if this was, say, a minus, we could not get rid of the fractions because there's no left and right side. The whole method of getting rid of fractions mandates that you have an equation. So please understand the difference between an equation and an expression and what you do with them. All right, so nothing to distribute, no like terms to combine. Because the 2/3 and the 1 are on opposite sides and you wouldn't want to combine them anyways. We're avoiding doing the fraction math because we can't for this problem, not the one I scribbled over a second ago. Denominators of 4 and 3, your LCD would be 12. Do you have to know how to do that? Please review online if you have to. One way of finding a common denominator is just to multiply all the denominators or all the unique denominators, but it's not always the least common denominator. Fortunately, it'll still solve the problem correctly, but you'll deal with bigger numbers along the way. So what I'm going to do is, every single one of these terms, I'm leaving some space because I'm going to fill in some number with a different color. Every single one of those terms, we will multiply by the LCD. We're multiplying all terms by the LCD. It doesn't say all terms with a fraction. It doesn't say just one side. It says all terms. So we take 12 times the x over 4. We take 12 times the 2 over 3. We take 12 times the 4x over 3. And yes, we take 12 times 1. This right here is where students make their mistake. They say, it's whole, don't do it. You still got to do it. Because this is us multiplying the entire left side by 12. This is us multiplying the entire right side by 12. So we follow that rule of whatever you do to the left, do to the right. I'm going to highly suggest reducing, that's an E, reduce first. This is not mandatory, but it is highly suggested. For problem C, it becomes mandatory unless you are really, really, really good at math and know how to avoid a particular issue. So this reduce first is a hint to avoid issues with more complex problems. So let's look at the middle term. Let's show you that it doesn't matter the order you multiply and divide. 12 times 2 is 24. 24 divided by 3 is 8. So 8's the magic number. 12 divided by 3 is 4. 4 times 2 is 8. It works either way. So why am I telling you to reduce first? First of all, it keeps the numbers smaller as you're processing them. Second of all, when we get to problem C, you can really mess things up if you don't do it that way. And that'll be for next class on Monday, unfortunately. So let's reduce this. The 4 goes into 12 3 times, so that's going to be a 3x. Again, 4 goes into 12 3 times, or 12 times x is 12x. 12x divided by 4 is 3. Plus 3 goes into 12 4 times. 4 times 2 is 8. Fractions are gone so far. That's great. Equals 3 will again go into 12 4 times, but 4 times 4 is 16, so that's a 16x. Then plus 12 times 1 is 12. No fractions. Hallelujah, praise math. Trust me, that technique is a miracle. It's amazing that it works. It's awesome that it works. And now we just do basically the same thing we were doing in the last problem. Add, subtract, multiply, add and subtract both sides to move things around because there's no distributions or like terms. So for the x's, me personally, and I'm not going to do it this way, me personally, I would move the 3x. I would subtract 3x on both sides, but I want to make sure you see an example of the other version of it. So maybe you're the student that just always moves the x's to the right, or excuse me, to the left. So you subtract 16x on both sides because the x's are going left. That means the constants go right. Plus 8 needs to move, so we subtract 8 on both sides. And again, do that in a second step if you need. So 3x minus 16x is negative 13x. The 8's cancel, bring down your equals. The 16x's cancel, 12 minus 8 is 4. So we have negative 13x equals 4. So we divide both sides by not just 13, not just 13, not just 13, because of the negative. We divide both sides by negative 13. I'm just going to, so I don't take up too much space, do a little arrow saying answer's going over here. So the negative 13's cancel, so we get x equals 4 divided by 13 definitely does not reduce as a fraction. But the only problem I have with this is negatives in denominators is generally not a great answer format. We either like them in the top or to the side. So x equals negative, let me draw that box a little better. X equals negative 4/13 is the answer. Again, 4 divided by negative 13 is the same thing, but the negative, just in terms of format, is best in front of the fraction or in top next to the 4. Both of those are fine, but my math lab doesn't always like the negative in the bottom. I don't always like the negative in the bottom. What I would implore you to do is start back from here, the 3x plus 8 equals 16x plus 12. Instead of subtracting 16x and 8 on both sides, subtract the 3x and subtract 12 on both sides. So the x's move right, the constants move left. You'll end up dividing by a positive 13 in the next step, but you will get the same answer. I guarantee it, unless you yourself make a mistake. And do I care which way you do it? No. 99.9% of the time, I am not going to care. Sorry, distractions. I am not going to care how you achieve a goal as long as it is a sound method and always works. If you get lucky one time and then it never works again, that's a problem. You need methods that actually work. But it is very rare that I'll say, you must do it this way or I'll take credit off. So that does not conclude 1.2, but that is all the time we have for today. So go ahead and start working on that prereq or review material homework assignment. Look at the files and stuff I put in Canvas. Start 1.2's homework if you can, but I'm not going to say it's due a week from today because we have not finished it. So we will finish 1.2 in Monday's class, and we'll definitely get into 1.3, but probably not finish it. Let me not say that yet because I gotta look. Either way, if you have no questions, we'll call it a day there. I am very happy to see that almost everyone, if not everyone, is in class live. So thank you very much for showing up. But I will still have this recording uploaded to YouTube no later than 5 p.m. today. And by the way, if you ever see me put a wrong recording in, it's probably because I was drained at the end of the day. I haven't done it yet, but I just know it's going to happen at some point. And I had to upload like all 3 or 4 of my classes at once for the day, and just copy paste mistakes happen. So please, just if I ever make any boo-boos like that, email me and let me know so I can quickly correct it. I don't think it'll be an issue, but anything is possible. Have a great weekend. Study hard, work hard, shake off that rust if any of this stuff is rusty to you. And yeah, take it easy. Have a good day.